So this slide looks daunting. First of all, it's telling us that we're going to start introducing polar coordinates to double integrals, and we haven't thought about polar coordinates for months. And secondly, that integral looks terrifying. And that integral is terrifying if you leave it as is. This integral's function here is to inspire us to try and find a way to integrate using polar coordinates, because as it turns out, this integral, once you convert it into polar coordinates, is really easy to calculate. All right, so since it's been a while, let's just review our polar coordinates. Remember that polar coordinates were just another way to get to a spot in the xy plane. And so we would have coordinates r comma theta instead of x comma y. So I might give you the point 3 comma pi over 2. And that would tell you to go find the angle pi over 2 in standard position and head out 3 tick marks in that direction. So we would go 1, 2, 3, and that would be the point 3 comma pi over 2. And we found that we could have just about any value of r and theta we wanted. We could have negative values of theta. We could have the point 2 comma negative pi over 6. All right, so negative pi over 6 means we go clockwise and look for pi over 6 or 30 degrees and go 2 in that direction. That would be that point down there, 2 comma negative pi over 6. And we could even have negative values of r. So if I decided to give you the point -1 comma pi over 4, we would find the angle pi over 4 in the first quadrant, but we would have to walk -1 tick mark in that direction, and that would get us down into the third quadrant. So pi over 4, -1 tick mark would land us there in the third quadrant. And then we had several formulas that we had derived that would allow us to convert back and forth between polar coordinates and rectangular coordinates. Right, so we had that x was equal to r cosine theta, y is equal to r sine theta. That comes from our SOHCAHTOA right triangle trigonometric rules. We had x squared plus y squared equals r squared. That comes from the Pythagorean theorem. And then tangent of theta is equal to y over x. And all of those formulas are going to be useful when we're converting double integrals from rectangular to polar coordinates. So how are polar coordinates going to make this beast a little less threatening? The first way you might recognize already, down at the bottom right corner, we've got this conversion formula that says tan theta is equal to y over x. Let's write that down. If tan theta is equal to y over x, then that means that theta is equal to tan inverse of y over x. And that's part of the thing that I've got sitting in that integral that's really ugly. So maybe we might be able to replace tan inverse of y over x with theta. That looks much simpler to deal with than tan inverse of y over x. Second thing is going to be our region that we're integrating over. Let's take a look at this region. I'm just going to graph that region so we can think about it in terms of polar coordinates. The x values are going from -1 to +1. It's probably the least threatening thing about this integral. And then y goes from 0, that's the x-axis, to the curve root 1 minus x squared. Let's write that equation down. Y equals 1 minus x squared under a square root, and see if we can recognize what that curve is. Square both sides, so I get y squared equals 1 minus x squared, and then add x squared to both sides. And we do recognize that equation. That's the equation of a circle centered at the origin. It has a radius of 1. So let's go ahead and draw that. Y is going from 0 to that curve, so it's the top half, kind of a semicircle. And that's the region that we're asked to integrate over. Representing this region is kind of clunky with rectangular coordinates because you end up with that square root of 1 minus x squared. It's really nice, actually, when we think about it in terms of polar coordinates, because that region is covered by all points in polar coordinates that have a radius from 0 to 1. So we could think about this as all the points that are trapped between an r value of 0 and 1. And then it's all of the theta values that range from 0 to pi. So in rectangular coordinates, one of our variables has to be trapped between a number and a function of the other variable. In polar coordinates, both of our variables here, r and theta, are trapped between two numbers. We know that integrals are much nicer when we just have number limits on our integrals. So our question now becomes, can we just swap out the variables? Can we just make this an integral where theta goes from 0 to pi, r goes from 0 to 1, where tangent inverse of y over x can just be thought of as theta? Can I just make this like dr d theta? So I don't know about you, but I would much rather work on that dr d theta integral than I would on the dy dx one that we started with. But the question is, can you just do that? Can you just change from dy dx to dr d theta? And the answer is almost. There is a little bit of something that you have to do to compensate for the change in variables, going from rectangular coordinates to polar coordinates. So we're going to get a little extra something in here that we're going to call a Jacobian that allows us to make this change. And we'll talk more about that in the next video.